Thank you, everyone. It's exciting to be here speaking about formal verification. The road to complete security of smart contracts is a very sensationalist title. So I'll spend the first couple of minutes sort of making a huge disclaimer on how this can only really be interpreted as either a very long and winding road or a very narrow sense in which complete security is actually achieved. But there is still a sense of completeness, and that's one of the aspects that I want to focus particularly on this talk. But as a start, I would just like to sort of set the context in which we're doing formal verification and the sort of assurances that one can reasonably expect from this type of procedure. And to do that, I would like to organize various assurances that we can have, not only of smart contracts, but of dApps generally, into a little bit of a taxonomy that involves at least four categories, or four flavors of things that you might want to protect yourself against. But first, let me just say a little bit about what formal verification is. Might not come as a surprise, but it is the process of specifying and verifying the behavior of programs. And so that's two aspects. So the first one is specification, which is writing specs. That's a mathematical description of the intended program behavior. And once you have a specification, you can proceed with the act of verification, which is something that has the following type signature. It takes the operational semantics of the language in which you're writing your program, and it takes the specification of what you intend that program to do, and then if they happen to actually conform, if the implementation matches the specification, you can produce a proof that this is indeed the case. And this is what is being done when you do formal verification. So yeah, let me talk about these four different flavors of assurances, or sort of problem categories that can exist in a decentralized application. To me, I like to think of them as being, the first one is really the parts that might be most common to formal verification as it is being done in other fields. It's really just looking at the bytecode. You know, if it's in the case of the Ethereum virtual machine, we'll look at the EVM bytecode, and we compare that with a specification that we have written in some higher level language or some mathematical description of what we intend this EVM bytecode to do, and then we can verify that it actually matches the specification. And so generally what we're talking about there is what can happen during the course of one transaction. And the second one is a little bit related to the first one, but we're talking about system invariance, and now we're not considering only what can happen over the course of one transaction, but what can happen over the course of many transactions, and in particular which system invariants or dApp invariants are actually in place in this set of contracts. And then there comes the really sort of nasty categories that we can't really, that are really hard and open-ended. So the first one of the sort of difficult categories, I would just call like blockchain-specific flavored assurances or problems that we might encounter. And this is a really open-ended category like Eclipse attacks, minor front-running or front-running by other actors, if your dApp is safe to chain reorderings, replay attacks, and all these sort of things. I mean, in many cases, you can provide assurances against them once you know, once you've actually thought of what they are and how they might present a problem to your particular dApp. Like if you want to protect against replay attacks, then you know, it might be very easy once you've done the specification to actually see that your contract is safe against this sort of attack. But to provide a formal method by which you can exhaustively check against all of these possible things that can go wrong with an application in the distributed setting, I think that's very difficult and very hard to make formal tools to do for you. And the last category is incentive reasoning, or sort of the game theory behind your application, and to make sure that the incentives that you expect the different actors in the system to act according to are actually well-founded in the game theory of the system. So if we look at how to approach these various classes of bugs or behaviors in a formal methods sense, then I'm gonna unlock my computer. Yeah, here we go. So here's what I would say is the efficacy of formal methods to approach these various problems. For the first two, it's very effective to use formal methods, especially when we're working with a sort of intricate virtual machine as the EVM, where there's really a lot of cases to consider, and accounting for various stuff is not a very creative pursuit, but there's still a lot of cases to explore, and it's really something that you want to make a machine do and not a creative mathematician or somebody that might have a more high level, might be skilled at different tasks, let's say. And for the second type of flavor, I would also say that it's really kind of effective. Some formal methods really start with these invariants, and then of course, you know, the formal methods are very effective at proving these sort of properties. For the methods that we are using with the K framework, these invariants come out at the second stage of the whole procedure, after starting with the first one as a sort of bonus. So they're not that difficult to prove, and the overhead of doing a formal analysis of the types of proofs or reasoning that you would make is a little too high with respect to how difficult that proof is. So I would say it's kind of effective. And then the last two are really difficult to handle with formal methods. The fourth one might have some interesting tools that can be developed. I know that there are a couple of frameworks that allow you to automatically find the Nash equilibrium of various games and stuff like that, but I haven't seen how well they could be applied to this particular use case of decentralized applications, but that would be super interesting to explore. And also there's a fifth category here that one might want to mention, which is ensuring the correctness of various cryptographic protocols that might be involved, and that's not something I'm even gonna talk about. Let's just leave that to the professionals. That's a little bit annoying. Okay, so going into depth into the first category when we speak about the verification of EVM bytecode. So for this talk, I'll mainly be speaking about the EVM, but many of the methods can be used to talk about different virtual machines as well, and I'll speak about that later. So if you remember the type signature for verification, we needed the operational semantics and the specification, and then we get the proof. So here's the operational semantics. The operational semantics of the Ethereum virtual machines, the Ethereum virtual machine has been defined in the K framework, which is a very nice framework for analyzing and designing and specifying programming languages and virtual machines using rewriting logic. And so the K specification of the EVM is also known as KEVM, or the Jello paper. And it's like an executable version of the yellow paper that passes the complete VM test and the general state tests. So it also discovered some faults in the tests, you know, some operations of the VM that weren't touched by the test. So it also expanded on what the tests were actually meant to do. And the beauty of K is that it's a very general framework that after you've defined a language in it, you automatically get these a suite of tools that you can use for analyzing that programming language. So already by having defined the virtual machine of Ethereum in K, you get a debugger and a symbolic execution engine and a prover and all these things. And so for our work, we're using the verification engine, which takes the following form. So K, as I said, is based on rewriting theory. And in rewriting theory, you usually deal with rewrites, and proofs also look similar to the rewrites of the programming language. So a reachability claim, which is sort of the nature of a specification, really, when you write it in K, takes the following form. You have this little rewrite arrow that looks like the implications arrow, and you say that S and then some condition on S and leads to S prime, and then some possible condition on S prime, or some property of S prime. And the way to understand this is that any pre-state S in big S, and now the reason why you can sort of speak about both small s and big S here is because you can abstract as many properties as you would like in big S. So we can think of big S as really a set and then a particular instantiation of a state that conforms to that more abstract version of the state would be a small s, being in big S. So any pre-state S in big S satisfying P of S will evaluate to a post-state S prime in S big S prime such that P prime of S prime holds. And then the proving engine is kind of simple in the sense that it just starts at this particular state and symbolically explores all of the possible paths of execution. And it either makes sure that all of the states that are being reached are conforming to the post state, or it tells you that your claim is actually false, or it runs out of memory or something. And what the state is here, the whole sort of configuration that we're speaking about, is the whole state of Ethereum, which is a large state. And when we want to prove properties of smart contracts, we usually want to, start with one contract and not talk about the whole blockchain entirely. So here comes the part of the whole process that DAPA MakerDAO that we've really added to this whole process, which is in making sure that this process goes a little bit smoother. Because if you're trying to write your reachability claims directly in K, they will be large and unwieldy. And just to convince you of that, here's a slide of how large and unwieldy it is. I would actually need a couple of more slides to fit the complete specification claim of what this little token transfer is actually doing. So let's look at how we would write the same claim instead. Here's a simple token contract. And we want to verify that the transfer function of this smart contract does what we intended to do, which is to increase the balance of the receiver and decrease the balance of the sender by the amounts that we want to transfer. So what you see on your left here is our specification format that we have developed that we call ACT, which is really abstracting away all of the parts of a K-reachability proof that are sort of boilerplate and not that interesting to the particular method that you want to prove. And it's a literal specification format that we think is fairly intuitive, and so it shouldn't be requiring too much explanation to see what's going on here. I'll just say something about storage. So this is, of course, referring to the storage of the smart contract in which this is all occurring. And the dash, the vertical bar dash greater than sign is the notation for the key value storage in this contract. And then the rewrite arrow is the equals greater than sign that we saw before. So this is really just saying that the balances of the caller ID is going to move from a variable that we call fromval to fromval minus value, and the value the balance of the receiver is going to increase by the same thing under the condition that all of the variables are not overflowing, because as you can see in the code, we have overflow safe arithmetic. And crucially, we also want to say what happens in the case where these conditions aren't being met. So when we take this act, we compile it to two k-reachability rules, which we call pass and one fail. And the difference between them is that we either assume the conditions in the if and only if clause to be true or false. And we say that in the fail case, the whole thing must revert, and nothing is going to be updated in that case. And then we add, if there's an if clause present, we add those conditions to both specs. And so in the fail spec, we also account for the case where we might run out of gas, but only if we run out of gas while the conditions of the if and only if clause are assumed false, which means that to really be covering the complete behavior of this method, we also need to generate two more cases, or really refine the passing case into a proper pass and a case where you have assumed all of the cases in the if and only if clause to be true, but you don't happen to have enough gas. And the reason why we need to do this in two steps is at compile time, we of course don't know what the gas expression is going to be, but after running through the proof once, since we're really exploring all of the paths, we get a exact condition for what gas really is in a case of successful execution, and then we can refine our spec to either assume that the symbolic value that we start with in our gas cell is equal to or greater than this expression or lower than. So if there is no if header present, then these three specs, the fail spec, the out of gas pass, and the pass, are going to be exploring the complete behavior of this method. Does that make sense? Cool. Okay, so that's one part of what KLab is. So KLab is one of the tools that we have developed in order to make the verification process of Ethereum smart contracts a little more intuitive and fun even. And the second part is a debugger. So as I said, K already provides you with a proving engine that you can see whether your reachability claims holds in. But it doesn't actually give you that much feedback when you try to run these proofs. It basically outputs true or false. And that doesn't help you very much if you want to verify some smart contract to just know that your spec is actually false. So we built a command line tool interface that allows you to step through what a K proof looks like. So you're really stepping through a symbolic execution of your smart contract. And that allows you to see precisely where things go wrong. I'll speak a little bit more, I think, later about how it can be used to explore unknown bytecode also. But just to give you a little preview, I was not brave enough to do a live demo of what it looks like, but here's just a screenshot that looks a lot like any Ethereum debugger, only that now you should notice that on the stack we have some symbolic values and not concrete instantiations. And we're also at a branching point, so we're able to explore multiple branches of execution by working with this little graphical interface. You know, we have hotkeys for exploring the state that the execution space of this method, really. Okay, so here's a little interlude from the formal verification side of things. I believe I was also asked to talk a little bit about how to write smart contracts so that they're safe and in particular provable. And here comes in a lot of opinion of how to write contracts. This is opinion that has been formed from of course, writing many smart contracts and working with it for a long time, but also looking at the formal verification process and see how you can make smart contracts as safe as possible. And so the first one I shouldn't even have to mention, keep code modular and as simple as possible, but no simpler than that. So the other points might be more interesting. If you're writing contracts that are going to be deployed on Ethereum, at least for now, for better or for worse, you're going to be working with the EVM. And even if you write your contracts in Solidity, the EVM is going to be what matters. So you should be thinking in EVM code when you're writing your implementation. Not at the design stage, then you should be thinking in whatever sort of paradigms that makes the most sense to you. You should be exploring many different ways of expressing what your contract should do and what your dApp should do. But when it comes to actually implementing that behavior in EVM bytecode, you should be thinking about EVM bytecode. The next point is a very opinionated thing, but I'm going to still propose it quite hard, which is that your methods, which is what I call the functions of your contracts, they should do one thing under the right conditions, and if those conditions aren't being met, then it should revert. And this is getting back again to how we write acts and how we write the specification of our functions. In almost all of our specs, we don't have this if clause. We only have an if and only if clause, which means that we only have to write one spec per method, and then we make sure that we have actually explored the complete behavior of that method. So if your methods don't do this already, then maybe rewrite them so that they do. Otherwise, you can just write more specs, but that isn't really the ideology that we subscribe to. Avoid calls to unknown code as much as possible. There's a lot of people that disagree with this point, but really, if you want to have strong guarantees about what your contract should do, then it's good if you know what the code of that contract is doing, because it's very hard to say anything about random code. And also, this relates to the point that you should be thinking in EVM code as well, which is even if your contract may look really sleek, if you use a lot of libraries and stuff like that, it hides a lot of complexity, sweeps a lot of complexity under the rug, and you should be thinking about the bytecode and not the Solidity code. And this slide is just to scare you, I think, of the fact that I'm really urging you to not write complex contracts, because contracts are complex enough as it is. This is a sketch of what multi-collateral DAI might look like, the various contracts involved. And this is actually as simple as possible, and it's still fairly complex, so we don't need extra complexity, so try to be simple. Okay, so the interlude is over. Let's go back to exhaustiveness and really what I mean by complete security of smart contracts. As I said, once we have written specifications for methods and we have made sure that we account for all of the possible cases, which in the best scenario is just one case, then we really have an exhaustive specification of the behavior of that method. And if we have that for all of our contracts, then we have a complete specification of the behavior of that contract. So if we do this for all of the contracts in our dApp, then we've essentially defined the behavior of that dApp. So the sort of non-standard models that I'm speaking about here is borrowing the metaphor of the standard models of arithmetic. After defining the axioms that make up arithmetic, you can also explore what models can satisfy those axioms in the same way that you can explore what bytecode satisfies the standard axioms that your specifications make up. And this gives you an indicator of how much coverage your specification and verification process really covers, because if you actually do this spec exhaustive well enough and you have complete description of the contract behavior, then essentially you should be protected against adversarial code. And by that I mean, if some code is written so that it matches your specs, then it should be as good as any code, and you should be willing to deploy that code as your application. Now, of course, there are some reservations there when it comes to gas, but the way that we write specs, we have abstracted this away, so it should really be as good as any code. So you think of the canonical implementation as the standard model of your dApp, and then consider the non-standard model of your dApp as any bytecode that somebody will use. And so this is something that we've been working towards continuously when we're doing a formal verification work, to really make sure that everything is exhaustive. And the ultimate test that we can make to make sure that they are is what I call a reverse bug bounty. And so that would be a process by which we ask for people to submit bytecode that passes our specs but still is faulty in some way. And now faulty is a little bit hard to define because our specs is essentially defining what is not faulty. But if there's still something that we have missed, then that would be great to know. So this would be like a bug bounty for our verification process, but it's really asking people to write buggy code instead of finding bugs in our code. Yeah, and when you have exhaustiveness, you can also do gas optimization. Let's see how I'm doing on time. It's pretty much up, so I'll only skim through system invariance. This is like the second flavor of assurances that you might ask for. And really, as I said, some people take this as the sort of primitive that they first try to verify the invariance of your contract code. But if you have this complete specification, you can essentially reduce the whole complexity of what your dApp is from this bytecode to the specification. Essentially, you can think of the specification as defining the atomic rewrites of a relatively small state machine. And now if you want to have higher level guarantees, then you can only reason about this relatively small state machine. And then proving these invariants is fairly simple. You just think of what may happen during the course of the lifetime of your contract as a list of calls, and then you can, by induction, prove that these invariants hold for these various calls. Here's a couple of invariants in the MakerDAO system that I don't have too much time to talk about. Let's just look at the one fundamental equation of die. It's kind of nice. Okay. So here's some things that we want to do in the future. Some particular point that I'm excited about is WASM support. We're currently, as of very recently, starting to work harder on doing a K specification of WebAssembly, and that's really going to be one of the first steps into having formal verification of smart contracts that compile to WebAssembly when that gets deployed. So I'm really excited about that. Oh, let me just say something about this exploration that I hinted at before. So what you can do once you have these reachability rules and this symbolic execution is that you can essentially write a reachability claim where the post state, so the right-hand side of the rule, is something that you're never really going to reach. And the prover is still going to operate in the same way. It's going to start at your pre-state and explore all of the possible paths, and until it reaches the end of the execution, it's going to tell you that your proof is wrong. But that doesn't really matter because we're interested in what the actual proofs, what the proof did explore, so the paths that we went through. Because if we have some unknown bytecode, for example, this is going to allow us to investigate the behavior of this contract and reverse engineer it or see what it does, really, from a symbolic point of view, which is a very interesting thing, I think. Yeah, and I think I'm out of time. Here are some resources. Thank you very much.
Thank you very much. We have time for maybe one quick question. If anybody is dying to ask something, just raise your hand. All right, we got one over there.
Okay, hi. So I had a question about, let's see. Okay, so Rice's theorem states that all non-trivial semantic properties of a program are undecidable in a Turing-complete language. So how do you actually formally verify a Turing-complete language like the EVM bytecode or Solidity? And aren't these reachability relations just accessibility relations, which are only valid in the Turing incomplete subset?
Yeah, so that's a good question. First of all, we do have the notion of gas, and for any finite value of gas, the execution is actually going to halt in the Ethereum virtual machine. So whether you think of it as being Turing complete or not is a matter of interpretation. But also, when it comes to verifying applications, we're always verifying a very particular subset and a program written in a Turing-complete language, and so that doesn't have to be Turing-complete at all. You know, it just has to do the things that we ask this program to do. So we're not really verifying the EVM as much as we're verifying an application written in the EVM. And then there are techniques of proving properties of code that contains loops, and the process is known as co-induction. And it's quite an interesting thing. But there you actually do have the property that when you do a proof with co-induction, you're proving that either the code loops forever or it exits in this particular state that you have specified. But for the Ethereum virtual machine, we still have the notion of gas, so everything is relatively finite. And that is to say that it is finite.
All right, let's thank our speaker once again. Thanks, Martin.